and welcome to another episode of That's Absurd. Please elaborate, the science and, well, we try to be funny podcast, where we take questions from you, the audience, or other hosts, or each other, and we actually dive into the science behind them, no matter how ridiculous, absurd, outlandish, or just downright silly your question may be. I am one half of your hosting peanut butter and jelly sandwich. I think I'm the jelly. I'm Julian Huguet, and the peanut butter is away today. Trace Dominguez is in the middle of a cross-country move, but don't you fret, because we have a very special guest host here to try and fill his surprisingly tiny shoes, actually, when you see them up close. She is a PhD astrophysicist and also PhD in astronomy, although she's got caveats to that. We'll talk about it. She runs Nora's Guide to the Galaxy. She's a science communicator and longtime listener of the show, apparently, so no pressure. This is Dr. Nora Bailey. Welcome to the show.
Hi, Julian. Thanks for having me. I don't know that I can fill Trace's shoes, but I will be myself and not Trace.
I'm telling you, they are, you see them and you're like, those are disproportionately small. You'd be surprised.
That's funny, because I actually also have disproportionately small feet, because fun fact, I'm 6'4", so you would think I have like huge feet, but I actually wear a size 10 in women's, which is like not what you would think for someone that's 6'4", which
that's quite small.
Yeah, and I think this is why I have a lot of feet problems. My feet can't handle it.
You'd be 6 inches taller than me with a shoe size that translates to 2 sizes smaller. How's your balance? Do you tip over easily?
Very much not good.
I think I found your problem.
Yep.
Well, welcome. Delighted to have you. As I teased, right, we were just talking before we got on about how you've got the PhD in astrophysics and astronomy, but you get more mileage out of the astrophysics one, right?
Yeah, because our department was like the Department of Astronomy and Astrophysics. Yeah, like I said, I don't consider myself an astronomer because I cannot use telescopes and I don't really know how to work with real data. So hats off to them who can do that.
So I'm actually really delighted to have you on. When we launched the show, or like even before we launched the show over a year ago, you were one of the very first people that I mentioned that we were making this. And you were like, oh, that sounds cool. And then you actually were like telling me like, I enjoyed this episode. And now that I have you on, I have to ask, and I'm so terrified of the answer, but like, how are we doing?
Yeah, I think you guys do pretty good. Obviously, a lot of it's outside of my area of expertise because I don't know anything about biology, and you do a lot of biology ones. There's been a couple physics ones that I were like, yeah, I think this makes sense.
Okay, so as long as we're outside your area of expertise, we might be doing well. Okay.
No. I think you guys do great on the physics ones too, so.
Yeah, that's funny. And yeah, Nora, no swearing like a sailor on the show. It's family friendly.
I know. I'm doing my best.
You have to fight that.
I know.
I don't want to spoil it, but we will get to your connections to like nuclear powered ships.
Spoiler
later
alert.
In this episode. I know. I kind of can't contain my excitement. But first, I think I'm going to kick it off. Since you're the guest, I'll just lead in with the first question that we have this week. And it actually, we have a recording from our audience member.
Ooh.
Hi, this is Aaron from the Kansas City area, and my question is, what is the maximum number of faces you can fit on a polyhedral die before physics says it's actually a sphere? This question came to me as I was wandering around my friendly local game store looking at all the shiny math rocks that I want to buy, but should definitely not. One was a D100, which is notorious for taking forever to stop rolling, and the question came from there. If we took a die, maybe the size of a Granny Smith apple, so it still fits in your hand, how many faces could you fit on it? Would it need to be made of a specific material to maximize that number of faces? If so, how much would it weigh? How well would it roll? Would it even be a fair, or fair enough, die? Thanks. I look forward to hearing your answer.
Well, thank you, Aaron. Nora, do you play tabletop games at all?
I did a couple times when I was like, in middle school, but I don't have a group, now as an adult, but I do know the many-sided die.
It's so hard to find a regular group as an adult. I hear you on that. I got kind of roped into D&D in college against my will and found out that I was very good at it.
I feel like that'd be something I'm good at because I am a writer and I love like fantasy. So, I should love it. But I'm also just massively introverted. And so like, it's scary to think about spending that much time with other people.
Here's the thing though, nerds, I don't know if you know this, typically an introverted bunch.
True.
This is my take on introverted people, is they're very quiet. If it wasn't obvious, I'm very extroverted. but like the funniest people I know are people who are like locked up tighter than the drum when you first meet them. And then when you get to know them, you're like, you're secretly hilarious. My wife is one of those people. Like a lot of introverts I know are just like the funniest people. And I think when they're finally in a group around a table playing Dungeons and Dragons, I think that's why it's so hilarious. They can cut loose and get into character. That's just a personal pet theory. But Aaron, let's talk about this geometric problem that you have posed to me.
Sounds like topology to me.
Yes, I was going to say that. I was going, not to split hairs, but I don't know if physics specifically is really like what would define what a sphere is. You're exactly right. It's more of a topology problem and a mathematical question just straight up. And I ended up diving into the mathematics of dice and was kind of shocked at what I found. So first of all, let's start with like the classic D&D set of dice, right? You've got a 4-sided die, or they're all like D4, D6, right? However many sides they have. So you've got a D4, a D6, a D8, 2 D10s, a D12, and a D20 for a total of 7 die, right? And that's your typical D&D basic set.
Where does the D100 come into it?
Well, you know, you can get really zany. So the 2 D10s are supposed to represent when you roll probability. So one of them is numbered from like 00 to 90. So that's your first digit of, you know, your percentages. And then the other is 1 to 10. So you roll these 2 D10s together and you get a percentage. Now, if you wanted to replace that with a single die, you would need a D100. But let's go back to the basic dice and those other 5 besides the D10. So it turns out these are all actually typically in a normal set that you would get for your D&D campaign. These are all very special shapes. Have you heard of platonic solids?
As in Plato of philosophy?
Yeah, not like we're just going to be friends and not have a deeper relationship solids, but like...
No, I don't think I have specifically heard of that, no.
So it is a geometric concept, and it's shapes that are made of regular polygons. So all the angles are congruent, all the edges are congruent. It has the same number of faces that meet at each vertex or point. How many platonic solids do you think exist? Knowing all the shapes that shapes can take.
I mean, you could just go up to anything, right? You could have any number of sides on a polygon.
Right, but that meet these specific requirements, right? It's got to have regular polygons for the faces, right? So all the angles are congruent, all the edges are congruent, and the same number of faces have to meet at each point. How many do you think satisfy those constraints?
I have no idea.
Do you want to roll a die and want to roll a D100?
Yeah. So, well, because a D100 has 100 sides, but the face on it is not a 100-sided face. It's like...
Well, it can be like, you know, a bunch of triangles stuck together, right? Or like a classic 6-sided die is an example, right? Like a cube. It's just a square, so it's a regular polygon, and then at every vertex, the same number of polygons are meeting. So on a cube, it's like 3 at every vertex meet.
I don't know, 20.
You're about 4 times too high.
Okay.
There's just 5.
Really? It only goes into a pentagon. Okay.
That's it. There's 5 platonic solids. And they are, aside from those D10s that you need in your set of 7 D&D dice, they're the other 5 dice.
Okay.
Your tetrahedron, your D4, your cube, your octahedron, your D8, your dodecahedron, D12, and your icosahedron, which is your D20. And that's it.
Wait, so what kind of polygon is the face of a D20? Is it a pentagon?
D20 is actually all triangles.
Really?
The cube is squares, the dodecahedron, the 12-sided shape, is pentagons, and then the others are just triangles.
Oh, cool. I had no idea.
I know. I was shocked. I'm like, 5? That can't be right. There should be so many more. No, mathematically, they have proven that there are 5 platonic solids, and
Math
that's
is so
it.
cool.
And they happen to be 5 of the 7 dice in D&D, which I think is so cool and so nerdy. So the cool thing about these shapes, these platonic solids, is ideally in their, perfect state, I don't know, you might say like their platonic ideal, they would also be fair dice. Because it's never going to favor landing on one particular side. If all the sides are the same shape, if all the edges are the same length, if all of the, vertices have the same number of faces meeting, then in a perfect world, when you roll it, you should get an even distribution of the numbers, across the board. No one particular number should be favored over any of the others, right? Now, when we start talking about bigger dice is when we start running into problems, because since there's only these 5 platonic solids, it's really difficult to make fair dice that are more than these 20-sided shapes. So, first of all, I want to talk about when he says, like, oh, how long would it roll, and why does it keep rolling, I think is kind of an unasked question in that. And I was being a bit sneaky when I alluded to your height and your shoe size, because that actually is directly related to what I wanted to talk about with dice.
Nice. I like the connection.
I know. When I thought of it, I was like, oh, I'm going to sneak this in there. But in physics, as I'm sure you know, right, things are stable if the center of gravity, which is basically like the average point on some object where like all the different little particles, like where their mass basically averages out to, if the center of gravity is over the base, you have something that won't tip over. But if you tip something to the point where the center of gravity goes beyond that base, right? And now gravity is pulling down outside of where the base is making contact with the surface, it falls over, right? And I think this is intuitively understood with, a bowling pin is a tall, skinny thing, and it just has to tip over a little bit and it flops. But if you have something short and squat and the center of gravity is low and the base is wide, it's really difficult to tip it over. It takes a lot of effort. So part of the problem with your D100s, along with them inherently not being fair, with it basically being impossible for them to be fair geometrically, is as you add more and more sides, the base that's in contact with the ground gets smaller. So it takes less and less and less of a lean angle for the die to keep rolling, to tilt over and keep tipping. Now, there have been efforts to remedy that in some very clever ways with dice. And there is the Zocchihedron. So a Zocchihedron is a 100-sided die invented by Lou Zocchi, and his goal was to make one that didn't keep frickin' rolling forever. And so he's updated it and refined it over the years, and it has inside of it like free moving weights. So they settle the center of gravity lower. So if the center of gravity is lower, it needs more of an angle to keep rolling, so it stops rolling as quickly. I think that's pretty clever.
That is cool.
Yeah.
Wait, so you said a D100 die can't be fair?
It can't.
Like, how unfair are we talking?
So, as a matter of fact, with the first Zocchihedron, nerds, because they are nerds, did tests to find out how fair it was. And they discovered that the lowest numbers on the die and the highest numbers on the die, like between 1 and 9 and between 91 and 100, they were rolled much, much less frequently than the ones in the middle. And it had to do with where Zocchi had placed the numbers. He put them by, basically, if you can think of the die as like a planet, he put them, the low and high numbers around the poles, and then the in-between numbers, closer to the equator. And just because of the shape that he made, those were more tightly squished together. And so, yeah, the distribution was wrong. So rather than amending the shape, though, Zocchi on future models moved the numbers to be more evenly distributed between the poles and equators instead of like the gradient that he had, basically, to just make the die kind of artificially more fair, which I thought was kind of cool.
That is cool.
Yeah. Oh, you know what's another great thing to talk about with platonic solids, since I have you as a PhD in astronomy? You know who a major figure was who theorized that platonic solids had some kind of deeper meaning for astronomy?
Ooh, I don't even know what century we're talking here.
What's 16th and 17th century?
Okay, I'm going to say Galileo.
Not Galileo. He was
Tycho Brahe?
German.
Kepler?
Yeah, Kepler.
I love Kepler. My subject area of my PhD was planetary dynamics. So
Did you come across this with Kepler at all? And
I
platonic
did not,
solids?
no, but me and Kepler's laws.
Oh, yeah. I mean, he's big. He's still huge, right? Those three laws are like so fundamental to how we still understand the motion of planets.
Yeah. And like the data that he had to like infer those from is very impressive.
Yes. Oh, it's amazing what mathematicians and astronomers did before computers. And again, I have things about that too. But as it turned out, Kepler, because apparently during this time period, the Great Enlightenment, people were very obsessed with, hidden things in geometry and mathematics and symmetries.
Numerology.
Exactly. And so Kepler theorized that the orbits of the planets were spaced out using kind of a system of these platonic solids, where he said, okay, imagine you've got the orbit of the Earth, right? And it's a circle. If you draw one of these platonic solids around it, I forget which one, but like the dodecahedron, right? If you could fit the circle inside the dodecahedron, and then you drew another circle around the dodecahedron, that's the orbit of Mars. Oh. And then if you draw a tetrahedron that could fit the orbit of Mars inside of it, and then you draw a circle around the tetrahedron, then you have the orbit of Jupiter, and so on and so forth. And he used this to basically because at the time, people were still divided whether the solar system was heliocentric or geocentric. Yeah. And he used this to be like, look, this works better with a heliocentric model. So therefore, because of these hidden harmonies, that must be the reason why it's heliocentric. And you're like, Kepler, I like you, but I don't think you're onto anything with this one.
I mean, he might be, because there might be it might not be a coincidence, right? There might be some mathematical connection that actually relates to the, power law that it really is. But I don't know enough about geometry.
I couldn't find it. To me, it just seemed like a little bit of like, we're just kind of going straight mystic on this one, aren't we?
Yeah, that's probably more accurate. Throwing things at the wall and seeing what sticks.
Yeah, why not? So there are, by the way, another category of solids that I think are really interesting as well. And these are Archimedean solids.
Okay.
And
Eureka.
Yeah, woohoo, that's the guy. And not unlike platonic solids, there's also a very limited number of these, but I'll tell you a little bit about what they are. Compared to the platonic solids, these Archimedean solids, they have faces that are regular polygons, right? So things like equilateral triangles or squares, that sort of thing. But they don't have to all be the same polygon on every face. And the vertices are symmetric to each other. So again, like each vertices looks the same as any other vertices.
Okay.
A great example of an Archimedean solid is if you think of the classic soccer ball, right? And it's got the patches that are like the black pentagons and the white hexagons. If you would flatten them so it weren't so spherical, that would be an Archimedean solid.
Yeah. What about I forget the what they call it, but like you can have a pyramid that's all triangles, but you can have a pyramid that has a square base. So would the square base pyramid be a Archimedean solid?
No, because the vertices would not all be symmetrical.
That's true. Okay.
The vertices at the point would not be the same as the ones around the base.
Yeah, it'd be the same number, but they wouldn't have the same angles.
Yeah. If you stuck those two triangles back to back, though, then you could have an octahedron, right? Or those two pyramids, and then you would have a platonic solid.
Yeah, okay.
But, so Archimedes, talk about somebody who figured out a lot of amazing stuff, including the volume of a sphere and how to calculate it before calculus was invented. He apparently, proved that there were a limited number of these solids. Do you want to take a guess as how many Archimedean solids there are?
12.
Oh! 13?
Oh!
So close. Pretty good. Pretty good. I'll give it to you. So apparently he proved it, and then the proof was lost, but just somebody else wrote about it that like, yeah, he totally did it. So you know who came along, though, and proved that there actually are only 13 Archimedean solids? Definitely.
No idea.
We've said his name already.
Oh, gosh. I'm trying to think of whose name I've even said. Galileo. But I don't think it was him.
No.
Tycho Brahe? No.
No, I love that guy, but he was probably too drunk with his pet moose or whatever.
Yeah. I don't know.
There's only one other guy that we've talked about. Who?
Besides Kepler, we haven't talked about anyone.
It's Kepler again. Yes.
Okay, I was like ruling him out from the start because we already talked about it.
I was so jazzed when I was reading about this because I'm like, I have a legit astrophysicist astronomer who's going to be on. And I'm like, I wonder if she's going to know that this guy apparently was also obsessed with these really weird shapes.
No, but I'm so impressed.
Yeah, it was Kepler who went and did the math and showed, sure enough, there are just 13 Archimedean solids, like basically that soccer ball shape that we talked about. So I thought that was really fascinating. But anyway, as we add more and more sides, though, even though they can't all be perfectly fair and regular, as we add more and more sides, like Aaron implies, yeah, we are getting closer and closer to a sphere. This might be easier to see in 2 dimensions, right? If you draw a circle and then you put shapes inside of it, like a triangle, it's not a good approximation of a sphere. But then a square is a little bit better, and then a pentagon's a little bit better. And so as you add more sides, you get closer and closer to a sphere. And so we start actually basically kind of rubbing up against a fundamental idea of calculus. And that is that as we approach a limit, right, like we get better and better at approximating this thing to the point that it is basically indistinguishable, practically.
Delta X becomes DX.
Yes, that's exactly if you were to write it out. Yeah. But the thing that we have to approach in terms of number of sides to make a sphere is infinity.
Infinity,
right?
yeah.
We have to... There is no real limit on how many sides we can keep adding to this shape to make it more and more
But there is in the real world,
sphere-like.
and I guess this gets back to Aaron's point about like what material it would be made of, because at some point it would be like the size of a molecule, right? Like
Right. There's no perfect sphere in the world, and I'm so glad you said that, because I'm going to talk about that too. So as you add more and more and more sides, it becomes more and more sphere-like. But here's a fun paradox that I kind of hit upon, and that is, how many faces does a sphere have? A perfect sphere in a perfect world.
Infinite.
Does it have infinite, or does it have 0?
That's a good question. I guess it depends on which way you're approaching it.
But it's funny, like we're kind of getting at. We're approaching infinity in faces to get more sphere-like, but I looked up mathematical definition of a sphere, and if we're talking about flat faces, it's 0.
That's true.
So you get more and more sphere-like, and also mathematically less sphere-like as you approach infinity sides, which kind of broke my brain a little bit. But you did mention, you alluded that in the real world, right? It doesn't matter. At a certain point, you're going to hit a fundamental limit on how small the sides can be. And that means that they're, going to be atomic in size, but they're still like, they have a measurable size. Yeah. And more than that, you can't make a perfectly rigid solid.
Okay, yeah.
I mean, perfectly, because I had this thought.
I believe that.
And that was, why do spheres stop rolling in the first place?
Well, it depends on the situation. If you didn't have any friction or air resistance, I mean, it's mostly air resistance because it depends. If you have sliding friction, then you get friction. But if it's purely rolling, there's no friction. So then it has to be air resistance. But
oh, okay. So you're going pure, but what if I put it in a vacuum and I rolled it like a marble on a smooth surface?
Well, then it wouldn't stop.
You don't think it would ever stop?
I don't think so.
I think, and I did a little digging in this, and I found people arguing about this, and I found basically some people concluding that because you can't have something perfectly rigid, that there's a little bit of deformation that takes place at the surface of the sphere and on the surface that it's rolling on. And because of this deformation, you get basically normal forces that aren't perfectly aligned with the center of the sphere, and these basically produce a torque that slows the ball down.
Interesting. Okay.
So even if you're on like something really smooth with a pretty hard ball, and discounting air resistance because it's a physics problem and we get to just say that and it becomes magically true.
You're cacao.
Yeah. Then at some point it should still stop rolling.
Interesting.
At least according to what I found. Now,
I believe it, but at the same time, if you are willing to hand wave away and say you have perfectly no air resistance, then how is it any different than hand waving away and say you do have perfect rigidity?
You're right. If you did have a perfectly rigid surface and a smooth surface for it to roll on that wasn't deforming, so yeah, I don't see why it wouldn't stop rolling ever. Let me go back to Aaron's question though. So what else does Aaron ask? Well, he asks how many faces could we fit on a die? So infinite. It's no bigger than an apple. What would it be made of? Well, that's basically dealer's choice, right? You can get dice made of plastics and metals. I do think these materials, though, will affect, in the real world, if we're not being, physics perfect worldy, they do affect how fair dice are. And I did some digging on real life dice that people use. And it turns out most dice are not fair, even if they are platonic solids.
Interesting.
Right? Because, you think of your typical six-sided die, and it's got little divots cut into it.
The pips, I believe they're called.
Yes, you're right. They're the pips. The pips, by the nature of the die, they have to have a different number of pips on each side. So you've taken a little bit more material out of, say, the 6 with its 6 pips than you have on the 1.
I thought they account for that when they make dice.
So a lot of dice, no. But in places like casinos, where there are, millions and millions and millions of dice rolls happening all the time over the course of its operation, and where it's very important that things be fair for gambling authorities to legalize it, they use special dice where the pips are filled in with pigment that has the same or as close to the same density as the material of the die as possible.
Interesting.
Yeah. But for a lot of us who don't care about that sort of thing, right, and we just go and buy a pack of dice to play, around a tabletop, they won't be fair. And if it's a 6-sided die that doesn't have any special, accommodations, it'll be weighted to land on the 6 more often. Exactly. So that's kind of nice.
Good to know.
You can see why casino wouldn't want that. How many
hundreds of times do I have to roll a dice for this to matter?
Many, right? I'm sure the distribution is still pretty even. I was watching, there was a mathematician named Percy Diaconis, and he was talking about some guy who just, as a hobby, rolled dice while watching TV and kept track of it all. And I'm like, who is this person?
I kind of love it, though.
Yeah, he had to roll it millions of times before he was like, oh, yeah, look, my dice isn't fair. But it's also not just the design of the die that affects the fairness, because there was one interesting thing that same mathematician, Diaconis, brought up when I was doing my research. And that is, what's something you notice about D4, D6, D8, D12, D20. All those dice.
Powered. Well, no. I was going to say powers of 2, but that's not true.
You're a little too advanced.
Yeah.
More simple than that.
The first thing that my brain goes to, because I do too much coding. But,
straight to logarithmic.
They're all even.
Yeah, that's it. Where are the odd-sided dice?
That's a good question.
Isn't it? I hadn't thought of that either. Diaconis talks about in this video he does with Numberphile, which has a ton of videos on dice, which was very fortunate for me. But of course they do, because mathematicians love dice, apparently. Yeah. But he talks about, okay, imagine I took a Toblerone bar, right? You know what I'm talking about? It's basically a prism. You got a triangle on each end and then a long rectangle for the other 3 faces connecting those.
Now I want chocolate, so.
Always. Me, forever. Right? If you were to just throw the Toblerone bar, it's never going to land with one of those triangular sides facing up, right? Because of the whole center of gravity and tipping it over. It's basically always going to land with one of the 3 rectangular sides facing up, right?
Yeah.
Now imagine you ate that chocolate with the sweet, the honey and the little crunchy bits in it. Oh, God. I love Toblerone so much. Anyway, not a sponsor.
I wish.
Imagine, Toblerone reps, get at me. But imagine you ate this Toblerone bar down until it was basically just a very thin triangle of chocolate, right? And now you basically flipped it as a coin. Well, now it's almost never going to land on those rectangular sides. It's going to land with one of those triangular sides face up, right?
With the longer axes.
Yeah. Well, therefore, there must be some point in between where you have a fair 5-sided die.
Interesting.
Right? But we have to live in the perfect world that is physics word problems for this to exist. Because Diaconis apparently did the math and was like, well, this 5-sided die that might be fair when I roll it on one surface, on a different surface, is not fair. It will favor either the triangular or the rectangular side.
That's a very unstable equilibrium is what you're telling me.
I think that's so fascinating. But I also love the idea of like an odd numbered die. It would be so
That would be really
cool.
fun. Yeah.
Yeah. But alas, I don't know. Somebody's going to make it now. Somebody's going to hear that and be like, challenge accepted.
You have to ship it with a surface. You get the die and you get the
That's
surface.
it. Or some way to, I keep thinking about the Zakahedron where he was like, all right, this thing keeps rolling forever, but I'll modify it with weights inside. Nobody said it had to be perfectly solid all the way through. I don't know. Maybe somebody will be ingenious in that way. Continuing on with the rest of Aaron's points, he asks, well, how much would this almost sphere polyhedron weigh? And I think it would be fair to just approximate it with the volume of a sphere. So take the density of whatever material it is, and then, multiply it by 4/3 pi times the radius of your almost sphere cubed. And there you go. There's your weight. So whatever you wanted to make it of, be it plastic, be it metal, it's not difficult to calculate.
I wouldn't recommend lead, and that's a little bit of a preview for what I'm going to talk about.
Depending on the game, depending on how radioactive the game is. Yeah, can you imagine lead dice just throwing it on the table?
It's very heavy.
Yeah, so it's not too difficult, but it would be basically your choice depending on how you want the dice constructed. But it gives me another chance to bring up Archimedes. That guy figured out how to calculate the volume of a sphere before calculus was invented.
That's pretty impressive. I did not know that.
That guy was really smart.
No, I believe that.
He did it. He was like, okay, let's imagine I have a sphere with a radius r. Okay, Now I've got a cylinder, and the cylinder has the same radius r, and then the height is the diameter, so 2r, right, of my sphere. Well, I noticed that if I take another shape that's basically two pyramids pointing at each other, right, where the points meet in the middle, if I look at the top of the cylinder, and I measure the length across the cylinder there, and then I measure the length across the top of my special pyramid hourglass looking thing, and add it to the top of the sphere, which is 0, it's equal. And then if I go to the middle of my cylinder and measure the length across there, it's equal to the length across the middle of the sphere and the length across that little itty bitty point where the two pyramids meet, which is to say 0. And he went, well, I bet that no matter where I go on the comparing the cylinder to my sphere and my two pyramids, the volume's going to be the same. And he was right.
Oh, wow.
And he said, okay, well, I know that a cone inside a cylinder is 1/3 of a cylinder. So therefore, the sphere must be 2/3 of the cylinder. And he was friggin' right.
That is very impressive.
How did he think of that?
I don't know. I'm
I have
horrible
done
at geometry.
so little with my life, and Archimedes was back there 2,200 years ago just being like, I'm going to solve this before the math that proves it is technically invented. And you're like, how?
You're just a few centuries too late to be...
Yeah. So when pretty much everybody else, when they're like, oh man, I totally proved it, and then it was lost to time, but please name these 13 solids after me, I'd go like, I don't believe you. But with Archimedes, I'm like, yeah, I bet he did that.
Yeah, I'll allow it.
I'll wait for Kepler to prove it. But I bet that he did that. He is him. He is that guy. Anyway, so Aaron, finally rounding out your answer, pun completely intended. Like we talked about, this isn't so much a physics question, it is a topology question. And it is basically, you can keep adding sides to an infinite number, which of course you can't get to, and you'll approach a sphere, but never reach it. It will become more and more able to roll. It will not be fair once you go past a limited number of sides, which apparently is just 20. But, doesn't really matter that much if you have infinite number of sides. I don't know. You're probably not going to roll it enough to notice a difference. It'll weigh whatever it is, depending on the density of the material you choose. And you could make it pretty much out of anything, so long as you can fit it in that shape. And we make spheres out of a lot of things. And would it be able to stop rolling? Not unless you cheated, like the Zakahedron, and put some weights in it, or had friction, or just had air resistance, and you're willing to wait long enough.
A long time.
But you might need a really long table
Yeah.
for air resistance to slow it down over the course of that time. But yeah, it'll basically roll until air resistance and deformation says it should stop. Do you think that answered it? Do you think we tackled it?
I do. I guess the only thing I'm thinking now is is there some way that you could say a certain material, if you made a face that was like, a molecule per side, like what material could you actually do that with? But I don't know how you would figure that out.
I guess you would need like smaller and smaller molecules or atoms.
What's the smallest molecule that you can actually like make something out of?
That's a great...
I have no idea what the answer to that would be.
That's a great question that I also did not look into, but because frankly...
But yeah, I think in general, the limit you would be approaching, I don't know how you would ever measure that.
Literally splitting hairs.
Like
well, much more than hairs.
Like,
millions of times
like an
smaller.
electron microscope or something.
Oh, this isn't as spherical as it could have been.
That makes me think of the episode you guys did with like the pointiest thing, where it's like at some point this loses all meaning.
It truly does. I guess the meaning would have to be you would need to be able to fit a number on it that you could discern in some way.
Yeah, it would have to still be considered flat.
Right.
So that's
right. Yeah, and it'd have to give you meaningful information, right? Because if you roll a die that's blank on all sides, like what does it matter?
Yeah, it doesn't. So
I guess that's really your limit of size. And then the question is, do you want to see it with the naked eye, or do you want to see it with an electron microscope?
Like loop. How do you pronounce that? Loop? Do you know what I'm talking about? Like the jeweler's thing.
Lupe Fiasco?
No, that I know how to pronounce. It's Loupe. It's a thing that jewelers use. It's kind of like a little like one-eyed microscope, and they use it to examine jewels. Anyway, it's totally
okay. I think I know what you're talking about. Yeah, I've only seen them in movies when they fall out of people's eyes when they're surprised with some shocking news.
This is a real diamond.
Right, when they're looking at the little thing and they see Archimedes' secret code written on this surface.
Yeah.
My God! And then Tom Hanks runs in with his weird mullet hair and solves a mystery.
I think we've really lost the plot here.
I know. I think it's perfect. I think this is. But Dan Brown and Toblerone, please contact me. I have an idea. Yeah, but going back to the pointiest thing, right? The needle that I found as the pointiest thing is used for literally moving single atoms around.
You could build a die with it.
To actually write stuff out. So yeah, you could have numbers written in atoms. You could do it.
That'd be a very interesting D&D game.
It would be very slow, but if you've ever done tabletop D&D, it normally takes forever anyway, because everybody's trying to romance the horse or whatever the DM's trying to get them to not do. So
nice.
That's my experience, at least. Yes, I was trying to romance the horse. I told you I was good at D&D. No, I rolled a 1 on that. I roll a lot of critical fails at the right moment. It happens a lot, actually. But it's the dice's fault.
Yeah, it's
clearly
not fair,
they're
as
unfair.
we have learned.
It's not fair. It's not fair. Must not be. Well, Aaron, thank you so much for your question. I hope that was a satisfying answer. We are going to take a quick break, and when we come back, Nora is going to share with us her answer.
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
You know, we think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages. They tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then, and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. Welcome back to That's Absurd. Please elaborate. I hope you had a good break. Took the chance to play a full D&D campaign and then came back. I'm sure it was brief, maybe a one-shot. Now that we're back, Nora, you have a question to share with us. What is your question?
I do, and I am so excited. When Julian was offering me questions, I picked this one in about 2 seconds.
It's true. You zeroed in on it. You were like, a lot of people get analysis paralysis where they're like, man, there's so many good ones. And this one you were like, that's a me right there.
Which would normally be me because I'm like horribly indecisive usually. But I am a very proud bunny owner. I love bunnies. I've had several pet bunnies. And I also used to be a radiation worker because I worked in the nuclear navy. And so when I saw a question that somehow managed to combine bunnies and radiation, I was like, I'm all in. I'm all in.
Okay, so let's actually hear the question. It's from Jarrett, and Jarrett sent in a voice recording.
Hello, Julian and Trace. I am Jarrett from Southeast Idaho, and my absurd question is, how much radiation would it take to kill a bunny, and what would a bunny have to do to protect itself from that radiation? I play a card game called Killer Bunnies, and there's a mechanic in it where a bunny can be inside of a robot suit that protects it from a variety of attacks. But this suit also slowly leaks radiation, and it harms nearby bunnies. It made me wonder, how much radiation would this actually involve, and what would this suit need to be made of to keep the bunny inside safe from the radiation without risking its health through anything like lead poisoning? Thanks, guys.
Awesome. Thanks, Jarrett. Sorry, I'm not Trace.
That's got you all over it. No, this instance, I can't imagine a better person to happen to be filling Trace's, again, abnormally tiny shoes to actually answer this. So, based on your bunny having experience and your time actually working around nuclear reactors, which I can't believe I got to say that and you're on this show, what did you find?
Yeah, so, okay, I think the question on its own versus the question when you add in the context of, like, the game and the mech suits are, like, very different. So, okay, so I think there's a few ideas probably to touch on here, which is one is, like, how does radiation even kill something? Because in general, the way that radiation harms you is it damages your cells. And at lower levels, it just damages the DNA. And over time, those cells may or may not repair themselves correctly. And so this can lead to things like cancer. But this is all very stochastic. So it's very random. And it's really difficult to say this exposure to radiation led to this cancer, you know, however much later. It just increases your risk. So it's like, yeah, it's just statistical.
You have to
basically.
look at, many cases to start pointing out connections. And just because it'd be like, oh, statistically, people exposed to this much radiation get cancer at this much higher rate than other people who do not get exposed to that much radiation.
Exactly.
Right?
So, but if you get enough radiation, then it can actually really quickly kill you. And this is something that's called acute radiation syndrome. So if you get a really big dose in a really short time, it's still the same thing. It's still damaging your cells, but it's not just damaging the DNA. It's basically destroying the whole cell. So the whole cell dies. And there's like different levels of this. And at the very worst level, it's your whole circulatory system collapses and you get increased pressure in the brain. And this is called the neurovascular subsyndrome of acute radiation syndrome. And that will kill you.
You know, I thought acute radiation syndrome was a radioactive bunny because it's so cute. But this does not sound cute at all.
No, this sounds horrifying.
Why would they call it that?
I know.
What's cute about it? I don't get it.
Nothing is cute about it.
That makes sense. You know, I don't think I'd ever really put together the full, like, I understood the damaging DNA and the long-term damage. But yeah, of course, like, a lot of radiation ripping through your cell is just going to destroy the cellular machinery that keeps the cell itself alive.
Yep, exactly.
Yeah, I get that. Okay.
So I think kind of the obvious question then is like, how much radiation does it take to get acute radiation syndrome? So I think that's somewhat of the wrong question just because there's some different concepts that are at play here. So there's radioactivity, and radioactivity is like the actual like rate that something releases ionizing radiation. So that could be alpha particles, beta particles, or gamma rays. Alpha particles are just helium nuclei, 2 protons and 2 neutrons together. Beta particles are just electrons, sometimes positrons, mostly electrons, and then gamma rays are photons.
Right.
So then that rate of decay is measured like per second. And then, you know, different things have different levels of radioactivity. So everything from like, you may have heard a banana is radioactive. This is true. It has a very trace amounts of this version of potassium in it that is actually about 15 becquerels of radioactivity, which means 15 radiations per second, versus something like gram. Sorry. Yeah.
Yeah, I have a question.
What's your question?
So you said, right, there's these 3 types of radiation, right? Alpha, beta, gamma, and you measure it. Is there some like equivalence between the different types of radiation? Like
there is, and we will talk about that in a little bit.
Oh, okay. Okay, I'll wait.
Yeah. So the radioactivity is just measuring like how many times these get released. So yeah, a banana, 15 counts of radiation in a second. A gram of the element radium is 37 billion becquerels. So, there's levels of radioactivity.
That's a lot.
That's a lot.
That sounds like you'd need to go logarithmic for
exactly.
that.
But so that's just like the radiation that's being released. But what we're actually interested in is the dose that you're getting. And so this is how much of that radiation is actually deposited into yourself, or in this case, into the poor little bunny's body.
Oh,
I know. And,
okay, so that's a different unit.
Yeah, so this is a different unit. So there's multiple kinds of dose that you can calculate. So there's like the absorbed dose, which is just like a straight calculation of like energy deposited per unit mass. And so this depends on what type of radiation it is, and how likely it is to interact with the mass, because, radiation can pass through things. It doesn't necessarily interact with every single piece of matter it comes across. So in the US, we usually measure this in rads. The SI unit is actually called a gray, which is super weird. I'm going with rads here. But a gray is just 100 rads.
Is there a conversion between rads and gray?
Yeah, a gray is just 100 rads.
Okay, so wait, I understand why we still use, and if you listen to the podcast, you know that Trace and I absolutely rail against imperial units all the time. But I can understand foot coming from old England or whatever, and mile coming from the Roman Empire and all that, and just not getting updated when the rest of the world moved to metric. But there's no way that, like, metric didn't exist when people were discovering radiation and how to measure it. So why are we not do you know why we're not on the SI unit for radiation?
No, not exactly. So I will tell you, so we talked about radioactivity, and the SI unit for that is becquerel, which is named after a person. And I think that makes more sense because it just counts per second. But the actual US unit for that is called a curie, which is based off of that value from radium. So it's like several billion becquerels. So usually in the US, if you're measuring radioactivity, you're going to be talking in picocuries, because you're just like, that's the scale. But yeah, so I think it's mostly just a matter of like orders of magnitude. So since the rad is just a little bit smaller, it's 100 times smaller than a gray, so it's just a little bit like easier scale to talk about.
Okay.
And also, I think because a gray is also named after a person, I believe. And so to me, a rad just makes more sense. We're actually talking about radiation, but
unless it was named after like Dr. Rad, which is the most like 90s Ninja Turtle sounding name I've ever heard.
I love that. I should start going by Dr. Rad.
Dr. Rad! You are a doctor.
That's true. And I was alive in the 90s because I'm old.
Cosine, take that. Dr. Rad. Okay,
so we have the rad. The rad is just how much energy is being deposited per unit mass. And then we can take that and we can convert it into what we call an effective dose, which takes into account how much biological damage happens from that absorbed energy. And beta and gamma are both going to do less damage than alpha. Alpha particles, because they're really big and they travel really slowly, so they interact a lot more, they are going to cause a lot more damage. However, they're also a lot easier blocked. So, there's like a piece of paper can block alpha particles. So it's
oh, really?
Yeah.
Okay.
So, anyway, so there's all these different things that come into play. So it's not just a matter of radiation. There's density and which type of radiation, all this stuff. And so all this gets translated down into a unit that's called, in the US, a rem, or in the SI unit, a sievert.
Okay. By the way, I am so happy you're going over all of this, because I have done, articles and videos on radiation in the past, and looking into all these units, I'm like, wait, what is what? What is happening?
I know. That's why I think it's confusing, but it's kind of it's important if you want to know how much damage is happening.
Yeah, definitely.
So sorry that I'm giving a little science lesson here, but before I even get into the question. But okay.
Yeah, we're on to our 7th unit now for describe what radiation is doing.
Yeah, and the sievert and rem, it's the same thing. A sievert is 100 times more than a rem.
Okay.
So going back to the banana, remember we said the banana has a radioactivity of 15 becquerels. And if we translated that all the way down to rem, it gives you an effective dose of about 0.01 millirem. So very, very, very tiny, right?
Okay.
To give you some context, you'd get about the same amount of dose from about a minute cruising on an airplane at altitude. So
oh, okay.
Yeah.
Gotcha. So if I have a banana on the airplane, it's not a big deal.
Yeah, it's pretty negligible. So the average American gets an annual dose of about 0.62 rem. And this is from a lot of different sources. It's from food, airplane travel, like I said, that you tend to get a lot. So some of the people that get the most radiation are airline workers, that flight attendants and pilots.
Makes sense.
Because they spend a lot of time up in the air.
Is that all gamma radiation from the
No,
sun?
so that's from any source, but it is mostly going to be gamma radiation, just because, as I said, the more particle radiation is just stopped a lot easier.
Right. But if you're in an airplane, right? Is it from gamma radiation?
It's still probably mostly gamma radiation, yeah.
Okay, yeah, that makes
sense.
sense.
So it's mostly from, cosmic sources at that point.
Yeah.
But yeah, so the annual dose also includes things from like X-rays. You're going to get trace amounts of dose. You're kind of getting exposed to natural radioactivity kind of all the time.
Right.
Now, if you're a radiation worker in the US, you're going to measure your effective dose throughout the year. And then there's a limit. And the limit for a radiation worker in the US is 5 rem. So that's a lot. Like if you got 5 rem, there was an emergency situation, which happened. You would generally would never get anywhere close to 5 rem.
Are you glowing at that point, like cartoonishly, or is that not a thing? That's probably not a thing, isn't it?
Yeah, at that point, 5 rem, it's still pretty minor, which is why it's the limit. But it's still a lot more than you would anticipate to get, because something would go really wrong if you got dosed that much. Okay, so 5 rem is the annual limit for a radiation worker. The amount of rem that you need to get acute radiation syndrome that we talked about, it's 5,000 rem.
Oh, wow, that's a lot of rem.
It's a lot. You really need to get just like blasted with radiation.
Yeah. Just fully flash a nuclear reactor, walk up to it in a trench coat and like, wah! And then like, that's what I'm imagining.
Yeah, if you were like inside containment of a nuclear reactor, you might, but that would never happen. Don't do that.
Yeah, one hopes.
That's for humans, but we're talking about bunnies. Now, I will say I'm going to kind of like step back because I said effective dose is measured in rem. And rem actually stands for Röntgen Equivalent Man.
Okay, great. Because I was wondering about another unit that you hadn't brought up yet, and I was almost too afraid to ask.
Yes.
Where does Röntgen fit in all this? Because I've seen the show Chernobyl. The phrase 3.6 Röntgen, not great, not terrible, is on loop in my head all the time. Where does Röntgen fit in? Yeah,
Röntgen, that's a great question. Röntgen on its own, I believe, is like the same kind of measurement as a rad. It might even be equal to a rad. But it might be just for gamma rays. Yeah, sorry, I did not off the top of my head write that down or anything. But yeah, so rem is basically Röntgen equivalent man. It's like how much is one Röntgen or one rad going to do to a person.
Okay.
I don't know of any Röntgen equivalent bunny like Reb, right?
Because we haven't studied it. Because why would we?
So I'm just going to stick with rads, even though we know that's not exactly the right unit, but it should get us in the ballpark.
Would there be any reason you can think of why it'd be substantially different? We're both mammals.
No, yeah, I don't think so. Because it does depend. Like REM depends. Like it takes into account things like different organs have different response to different like radiation. So that kind of thing is taken into account. And we do have similar systems. I'm not a biologist, so I don't know how similar bunnies and people are. So it's probably very similar. But so we're just gonna use rads.
Okay, I will accept it.
Okay, but I just wanted to be clear about what we're doing here, because I know it's confusing. Okay, so then if you want to know how many rads would it take to kill a bunny, very sadly, there's actually a lot of studies about this, because rabbits get used as lab animals a lot.
Oh.
So yeah, you can literally find papers where they're like, we killed bunnies with radiation, and this is how much it took.
That's a hell of a title.
I'm not sure that was the exact title. I might be paraphrasing. So I found a couple studies for this. And there's one paper from 1962, and they basically found that a dose of 22,000 to 44,000 rad would kill a rabbit in a couple hours. And it would happen by inducing what's called hyperpyrexia, which is basically just the rabbit overheat. Whereas a dose of about 525 rads to 875 rads would kill them in a day or two. So it would definitely kill them, but it would take a little bit longer.
Yeah. How quick is your buddy getting roasted?
Yeah, exactly. Another study in 1967 found that a lethal dose for rabbits was 973 to 1,054 rads, so basically around 1,000 rads. But also this is going to vary from rabbit to rabbit, because rabbits, there's like a pretty wide range of rabbit breeds. Like you have like Flemish giants, they can be like 20 or more pounds, and you have like Netherland dwarfs that are like 2 pounds. Right?
Okay, so if you're bigger, can you absorb a bigger dose?
I think yes. That is my kind of somewhat educated guess, but
okay. All right.
Yeah. But it also depends on other things. So like there was a 2015 study, and they found that inbred rabbits were more susceptible to radiation damage than not inbred rabbits, right?
Oh, that would make total sense to me, because if they're inbred, then if they have like defective alleles, right, there's nothing making up for something getting damaged.
Exactly, yeah.
Yeah.
Yeah, and in this study, they were hitting rabbits with a 400 rad dose, and the rabbits had an average lifespan of 100 days for the inbred rabbits and 160 for the non-inbred. So 400 rads, still probably going to kill a rabbit, but it's going to take a long time.
Okay.
Yeah, a few hundred rads kill a bunny at some point. But if you want it to be like quick, if you want to be like, I am killing this bunny by shooting it with radiation, it's going to be more like 1,000 or more.
Okay. So I don't know the mechanics of this bunny game that Jarrett plays, but Jarrett, you want to surround your bunny in its radioactive suit. The adjacent bunnies need to be large and they need to have a healthy genetic diversity to them.
Yes.
So again, if the game mechanics allow for that, that's something to look for.
Yeah. So setting aside the game mechanics, if we just considered in general bunnies, like how would a bunny even get dosed with 1,000 rads? Because that's a lot. I mean, that's 100,000 bananas, which I mean, rabbits love eating bananas, but that would be a lot.
Yeah, this is still ridiculous. There's a limit.
Yeah, that's a lot. If you were to go to the present day red forest, which is the area near Chernobyl where like all the trees died, so they call it the red forest, the soil there still contains a ton of radioactivity, and bunnies tend to live in the ground, right? So they would get a lot of radiation from that. But even so, they would need to spend 10 weeks in a tunnel in the dirt in the red forest to get 1,000 rads of radiation.
Okay.
It's a very large amount. Now, obviously, the studies that they did, they obviously had a way to give a really big dose all at once. So that is the best way. I feel so bad like about killing bunnies, but that is the best way to dose a rabbit with a huge amount. So like in the 2015 study, they used like a cobalt-60 source that was just like, blasting them with a certain amount of radiation, per second.
Gotcha.
So,
okay.
How could a bunny protect itself from this sort of radiation? Again, setting aside the game, I'll talk about that a little bit later. But naturally, there's basically different ways of doing it. So there's something called a halving thickness. So this is basically if you have something in between you and radiation, the halving thickness is how thick that thing needs to be to reduce the incoming radiation by half.
Everything in nuclear science is all half this and half that.
Yes.
What is it with you in inverse logarithm?
Something about exponentials.
Yeah, exponentials, excuse me.
So, like I said, rabbits, they tend to live in tunnels in the ground. The halving thickness of packed dirt is 3.6 inches and of sand is 4.4 inches. So I don't know exactly what of loose dirt it would be, but, somewhere in between those probably.
Okay.
So if we wanted to reduce that 1,000 rad dose, you would probably need a tunnel that's 6 feet deep, and that would reduce it by a factor of 20,000 or something. So
wow.
Yeah.
Much more acceptable.
It goes pretty quick because we're talking about halving, so it gets exponential.
Okay.
So that's one way a bunny could protect itself. It could just go into its tunnel underground and it would protect itself from a pretty strong dose, I guess, of radiation.
Do you know if that's like a typical depth for like a bunny den? I don't know. I've never had rabbits.
I actually looked this up. So a typical wild rabbit hole is 3 to 10 feet deep. So
okay.
Yeah, so I think the factor of 20,000, I said if you would consider 6 feet deep and a halving thickness of 5 inches, which is like a little conservative since I said, sand was 4.4, that would be 20,000, a factor of 20,000.
Okay. Yeah, that sounds like at that point, maybe we don't really notice a difference between, the radiation exposed bunnies and a control group, right? The statistical difference kind of becomes indistinguishable.
Exactly. And then since dose, it matters how much radioactivity there is, like how much radiation, but also matters how much time you're exposed to it, right? So you're going to accumulate dose over time. So if you had a less powerful source or it was like going over a longer time, the bunny could just leave. Like that's a very effective strategy against radiation. Just get out of the area where the radiation is coming from.
Yeah. Yeah.
And this is, what they did near Chernobyl, right? They evacuated people. Like so the town, I don't know how to say this, Pripyat. So this was like less than 2 miles away from Chernobyl, which is like the worst ever nuclear accident like ever. And so they were less than 2 miles away from it, and they weren't evacuated for about 24 hours after it. And the like highest dose that anyone there got that they know of is about 38 rad, which is like obviously very bad, but like nowhere near 1,000 rad, right? So like you have some time to get out of the area before you're like being exposed to 1,000 rads.
Right. So we're talking for these people from Pripyat. Are we seeing more of the long-term higher cancer rates?
Yes, exactly.
Higher, but no acute.
No. The people at Chernobyl that got acute radiation syndrome were the people that were like on site responding literally at the reactor site within the first like couple hours.
Yeah, that makes perfect sense to me.
And also if, you had a person like in a lab shooting you with radiation, the bunny could fight back. That's a good method.
So there's that.
You know, bunnies are pretty strong they can kick very hard and they have little claws and they have little teeth. I've been bitten by a bunny. It's not very fun.
If you got bit by a radioactive bunny, what are the odds of becoming a superhero with a bunny theme? Is it
very low? I don't think
low.
I don't think that's how radioactivity works.
Okay. Well, I mean, maybe we need more data.
Good.
How many studies have been done on that? With like the radioactive bunnies get to bite somebody at the end.
That's true. That's a good point. I do not
know. I don't think we can rule it out just yet.
And I think like probably the like most powerful source, I guess you could think of radiation would be like a nuclear weapon going off. But in fact, at least for modern day nuclear weapons, the blast radius is such that you would be destroyed by the blast if you were close enough to actually get a large enough dose to have acute radiation syndrome. So, fun fact.
So, one less thing to worry about.
I guess. Yeah. So
that's great news.
Now, again, that doesn't mean that you wouldn't get like alarming amounts of radiation at some point, but you know, you're not going to get 1,000 rads, and you.
Yeah, you know, I'm too busy being vaporized to really care.
Exactly.
Oh, I also don't feel good. Oh, my cells, like.
Yeah, that was like a weird thing to research. Anyway.
Yeah, it's kind of morbid, but somebody had to do it.
I was like, oh, that's interesting to know. Okay, so I think that's like kind of like just general, how could a bunny, you know, protect itself and how much radiation would it get. But now if we want to consider this like specific killer bunnies with mech suits idea.
And I do.
Yeah, of course. So it sounds like we're like killing the bunnies pretty quickly because he said it was 3 turns. Now, I do not know how much time is associated with a turn, but assuming it's like an hour, I have no idea if that's even right, but I'm just going to assume it's about an hour. You know, we're probably looking at like 20,000 rads, right? Because even the 1,000 rads would take a day or so to kill. So you need like a huge amount of radiation. 20,000 rads, we'll say that. So that's based on that 1962 study. So he said that the bunnies can use these mech suits to protect themselves, which means that you don't have to think about packed dirt. You can think about something that has a really, really small halving thickness. And one of the things that is lead.
Yeah, I was like, I know you brought up the lead dice for a reason. Yeah.
And this is exactly why when you get an x-ray, like at the dentist, and they come in, they put that lead apron on you, that's because that lead will stop at like stray radiation from the x-ray. Which is, you know, better for you. It reduces the amount of dose you're getting from stray sources. So lead has a halving thickness of 0.4 inches, which is not that much, right? So,
no.
Yeah. So if we assume that this bunny needs to protect itself from 20,000 rads over some finite period of time, and it can't just run away, then we want to bring that down to a safe level. So I'll just say 5 rads based on the fact that a radiation worker has an annual limit of 5 rem. So that's what that's based on. So we need to reduce the radiation by a factor of 4,000. Which if you take log 2 of that, that means that you need to have it 12 times.
Okay, and then times 0.4.
Times 0.4. So you need 4.8 inches
4.8 inches. That's reasonable, although it'd be very heavy.
So he mentioned lead poisoning. You wouldn't really need to worry about that. You kind of have to ingest lead mostly to be poisoned by it. It doesn't really go through the skin.
Okay.
So unless the bunny's trying to eat its suit, which would probably have other issues, like, it's not going to have to worry about lead poisoning. But the bigger concern here is the reason that lead has such a short halving thickness is because lead is very, very dense, which means it's very, very heavy.
Right.
So if we assume the bunny has a surface area of 264 square inches, which would be like the estimated surface area for a body weight of 5 pounds for a rabbit. I actually found like a chart on that, which was kind of fun.
Was this from like taxidermists? Why would people be calculating the surface area of bunnies based on
it was
weight?
from a website called The Pet Oncologist. So somehow related together. Yeah.
Oh, so people who actually need to take x-rays and okay.
Yes, I think that was probably somewhat what it was. It was a PDF, so I did not have any context. So not the best source in the world, I'm sorry. You know, it gave me an equation and that was all I needed. So, okay, so we got 264 square inches and 4.8 inches of lead, which means that there's about 1,250 cubic inches of lead on this bunny. Now, lead has a density of 0.4 pounds per cubic inch.
Oh my.
Our bunny is wearing over 500 pounds of lead, which is over 100 times its own body weight. Now, I know it's in a mech suit, so like, sure, there's actuators and things to like help it, but that's got to be a really good mech suit to be able to support that. I don't really think that's going to work.
I wonder if this hypothetical bunny mech suit engineer was running into issues of like, okay, I need a reactor that provides more power because my lead encasement of my bunny is getting really heavy, but then I need more lead So they need a heavier reactor and then more lead, and eventually all the bunnies in the surrounding area are like wilting.
Yeah, they're just stuck inside these lead like sarcophagi at that point.
Yeah, and that bunny's like, I'm fine, I'm chilling.
Yeah.
What, you all didn't want to wear it? How many pounds of lead was it?
Over 500.
Over 500 pounds of lead.
Yeah. And then I thought, I was like, okay, maybe we're being too conservative by reducing the dose to 5 rads, because like 5 rads is like pretty low. So I was like, let's say we went to 100 rad, which we know would be like dangerous, but like definitely not immediately fatal. Then you only need 7.5 halving thicknesses, but that's still 330 pounds of lead. So it's just not feasible. It's just not feasible, unfortunately. And then I was also like a little confused about the mechanism here, because he said that you're wearing this mech suit, and the mech suit can leak radiation that harms nearby bunnies. And I was like, are the nearby bunnies also wearing mech suits? Because presumably the bunny that's wearing the mech suit needs to be protected from its own radiation. And if the other bunnies are also wearing mech suits, they would also have that same protection. So I don't understand how you would damage the other bunnies and not the bunny that's wearing it.
Well, hold on. Here's the thing, though. So you've got your halving thickness, right, for a set amount of radiation coming off of this reactor. But if you put other nearby reactors that are leaking close by, right, you're going to let more radiation through, right? So I still think mathematically, even putting nearby bunnies in mech suits would not necessarily keep them as safe as the limit that you've laid out.
That's true. I think you'd be screwed, bunnies.
Which, for bunnies, they're okay with that, so.
True.
Sorry. It's rabbit biology.
Yeah,
joke.
and because radiation follows the inverse square law, so the bunny that's wearing the suit is going to be getting a lot more radiation.
It is the most at risk.
Than the bunny that's wearing it. So like, yeah, I just couldn't think of a way that it would work for the bunny wearing the suit to not be the one getting the bigger dose and therefore be screwed.
Yeah. This is very unsafe. This is very Soviet-style mech suit of like, we don't really care about the safety of crew. They sacrifice themselves for glory of Bunny Nation.
If you're interested in committing some animal cruelty against the world's cutest animals, I don't recommend it, but that's what you would need to do. You would need to blast him with 1,000 to 20,000 rats.
You there listening to this podcast while tinkering on your mech, atomic-powered mech bunny suit. You stop it right now.
I actually did a little research into mech suits about this, because I was like, do we like actually have the technology to make mech suits? And the answer is no, not really. Like,
wow, you covered every angle.
Well, I was just curious, because I was like, because I know that mech suits, like, they're heavy, so they have to have a mechanism to support their own weight. So I was like, maybe it could support, 100 times its own body weight. But yeah, this mech suit. But I didn't think that was possible. I found one that someone had made, and it was huge. Like, it was like, and it still didn't have that much weight on it. So yeah.
Yeah. I always thought part of the problem too was just like the fine control of a mech suit isn't really possible either.
Yeah.
I don't know. I'm sure there's many engineering barriers that I am not qualified to speak on, but
I just I feel like a tank would serve you better in most cases. And like if you want to have, I suppose you could have some terrain, right, where like a tank wouldn't work super well then, but you'd probably still be better off with an autonomous or remote controlled robot than like, why would you need a person inside the suit? I'm not entirely clear on the benefit of that.
Yeah. If you could engineer a mech suit, you could probably make a remote control,
exactly.
like quadruped by that point.
Which, I mean, I'm a big sci-fi fan, so, I find that sad because I like to think about mech suits, but...
But there's just no need to sacrifice these bunnies in this needless way.
I was like trying to envision the mech suit, and I was like, are these bunnies bipedal, or are they like going around on all fours? Because it's a very different vision of a mech suit in my head either way, but...
Yeah. I don't know. I'd have to look up the game.
They have affordable hubs? Like, how are they operating these things?
Can you imagine this poor...
I maybe thought about this a little too much.
Try to play this at game night, and you've got all these questions. They're like, Nora, just roll. Just roll your 100-sided die already and get it over with.
See, I'm totally able to ignore the science of things and just roll with it for fun until I'm like expected to think about whether the science works, and then it all falls apart, and I'm like,
so you were explicitly asked by this podcast to look into it.
Exactly.
And then you went down a rabbit hole.
Literally, quite literally. Yeah, like if you're watching a movie that's clearly not meant to have any reality in it, totally fine. But if you're watching something like Gravity, and you're like, these things aren't in the same orbit.
What? She just like zipped over to the Chinese space station?
They're trying to make this so serious and accurate, and like, you're just making me think about the science.
I have a friend whose biggest gripe with Interstellar, he's like, really? Anne Hathaway thinks that the thing that can travel across the universe is love? Get out of here.
I was like so into that movie until that point, and all of a sudden I was like, what?
Stop it. No.
I was like, you did so well with the time dilation.
Everybody praises the black hole simulation. Ooh, and the time dilation. No, the love traveling across the universe thing is where I draw the line.
Just turn the movie off before that point.
Anyway, I've had it. Christopher Nolan. Gonna go watch an uplifting movie of yours like Oppenheimer.
Which was a very good movie.
It was a very good movie, but it surprisingly did not talk about Röntgen or Sieverts at all.
No, yeah, they really didn't get into like the radiation side of things. So
what were they thinking? The people demand to see that. That's what the Academy is interested in. I guess not everybody's like us, Nora.
I know. Sadly, I've known that for a very long time.
Yeah. Well, Nora, thanks so much for tackling Jarrett's question. It was really such a delight to have somebody who is so qualified to talk on this and really dig into all of this. I really enjoyed that ride, so thank you.
Thank you. No, it was a lot of fun, and I definitely went and gave Pippin some extra hugs after I did all that.
I would never put you in a mech battle.
I would not do that to you.
No, I wouldn't. Wonderful. Well, that is going to do it for this episode of That's Absurd. Please elaborate. Thank you for listening. The show was created, written, produced by me, Julian Huguet, and Trace Dominguez, who is, again, out as he does his cross-country move. Guest host Nora Bailey stepped in admirably for Trace. Nora, where can people find you?
Yeah, you can find me pretty much anywhere on the internet under Nora's Guide to the Galaxy. I have a YouTube channel where I do somewhat longer form videos, and I also do a lot of short form videos on TikTok/Instagram/Facebook. So yeah, come check it out.
Okay, and how do we feel about the alter ego Dr. Rad, which I assume will be your supervillain persona?
I think it'll be good, yeah.
I don't know, it's got potential. It was also produced and edited by our wonderful and well radiation shielded editor and producer Kyle Sisk. Special thanks to Jarrett and Aaron for sending in questions for this week's episode. If you would like to submit a question, look for the form in our show notes. Email us at hello@that'sabsurdshow.com. Visit our website, that'sabsurdshow.com/ask, or even call us on our Google Voice line 302-TAPE-SHOW, TAPESHO. If you leave a voice note, we'll feature your voice on the show, just like we did for both questions this week. Also, if you could leave us a review, stars, hearts, kind words, or I guess they can be angry words. I can't force you to leave a positive review. Please do that. It helps people find the show. And of course, send in more questions. They make us laugh and they make the show possible. Special thanks to those listening on Nebula. Nebula listeners get access to ad-free versions of episodes, and they can support us and other independent creators. To join Nebula, go to nebula.tv/that'sabsurdshow. And Nora, what do we always say at the end of every episode? If you don't radiation shield your bunny, you're really rolling the dice.
Ooh, I like that.
We say that at the end of every episode. I'm so glad it's finally relevant. It had made no sense up until this exact point.